Hey, good day, everybody. This is Mr. Benning, and we're going to look at starting a new section on cells. But in order to kind of talk about what a cell does, we need to go into a little bit of chemistry. So we've got a chapter of just some basic chemistry. Should be fairly simple concepts and stuff that you've probably seen or should have seen and heard before if you've had chemistry. So let's look at what we have today. And so we understand that all matter is composed of tiny particles called atoms. So this is what you should be able to do or should need to know for all this. So number one, we can identify the particles that make up us atoms. Wow, it should be up atoms. And you can diagram the particles that make up the atom. You can compare covalent and ionic bonds. And you also should be able to look at van der Waals forces. So if you don't remember some of that stuff, this would be just a nice little refresher for you. So the first thing you need to look at is that atoms are the building blocks of all matter. So when we talk about atoms, everything in the atom makes up everything. We're talking me, you, the chair, the desk, the TV, whatever you can think of, it's made up from atoms. So now, so any substance, just like I was saying before, that you can think of is comprised of atoms. Whether, like I said, from anything from people all the way to the chair or whatever. So let's look at the structure. So we've got a basic structure here. So the nucleus is the center of the atom, and it's got neutrons and protons. Okay, so that's where they live at. The proton, you will see it as a P plus, is a positively charged particle in the atom. And the other one that's in there is the neutron. You list it as an N0. Is the particle that has no charge, but a lot of scientists say that it emits the strong nuclear force, which keeps all the protons together. But we'll go in. That's for your chemistry class. And you can deal with that. So later. And so surrounding the atom, though, in the orbits around there is the electron. And that's a negatively charged particle, and that allows for, the bond. That's what uses the bond. That's what moves from atom to atom. The nucleus does not change if the atom is stable, and there are 92 of those two elements that have stable atoms, and we'll talk about that later. And so the mass of any atom, the electron is so small that we'll go into this real quick. The mass is only based on the proton and the neutron. And they are so much large. The reason we just say that is because they're so much larger than the electron. And so the electrons have no effect on everything. So it takes about, the last number I said was about 1,000 electrons is the same mass as one proton. Okay? And that's why we don't count them. They're so small, it doesn't really contribute to the mass. But it does contribute to the charge, because remember that protons are positive, electrons are negative. So if there is the same number, we'll talk about that in a minute, about ions and stuff like that. So again, the elements. So elements consists of atoms of only one type. I don't know why that is there, should be gone. It just consists of atoms of only one type. So, like, for example, if I've got a bar of gold, for example, Au, gold, it's all the atoms will have the same number of, not neutrons, but protons. Because the protons determine what the element is. So the elements are determined by the number of protons, as I just said, that are in the nucleus. Right now, and I have, again, according to IUPAC, which is the official chemistry group, there are currently 118, with 118 being the most recent one of known elements. And that was done within the last few years. They've not made 119 yet, and they're kind of, that's something you can talk about with chemistry later. But they're kind of excited about all what's potentially coming up in the new elements. But of the 118, only 92 are found in nature. So everything from, if you look at the periodic table, starting with hydrogen, going all the way to uranium, those can be found in nature. Anything outside that, like plutonium, americium, californium, einsteinium, I forget what 118 is off the top of my head, but that one is but those are no longer found in nature. So here's the periodic table, and so like the elements so like these, all of these not found. So a lot of those outside of that are just not in nature, and they're man-made. So most of these exist less than a microsecond, especially the heavier ones. So let's look at so a couple things you might want to look at. If you look at the top here, you got group and period. The rows are called groups. They're called periods, because the periods deal with energy levels, and the columns are called groups. And those deal with the number of valence of the outside electrons. And that's something, again, we may talk about later. An isotope, so sometimes a lot of elements have isotopes. So an isotope, okay, is an element that has the same number of protons and a different number of neutrons. So I've got a picture over here with carbon 12, carbon 13, and carbon 14. And so we list the mass 6. So like carbon 12, which is the one that's most commonly found in nature, has 6 protons, 6 neutrons. That's the most common way to look at it. And then the next one up, you've got carbon 13, which knows the protons don't change, but the neutrons do. So I go from 6 to 7 neutrons, and whereas carbon 14 will have 8. Okay, so again, the number of neutrons change. Well, and you notice there's a lot of information at the bottom of carbon 14 talk about half-life. Half-life means it's radioactive. It means it's unstable. Meaning, so like example, like carbon 14, it, like what I just said, it's an unstable one. Isotope, meaning that they will decay or split apart into other elements. So what happens here is that this here, one of the neutrons, because what a neutron is a proton and electron combined together into one proton and one electron. So it does, it's what we call beta decay. That's something you might want to look at later. But it changes it. Eventually will change into nitrogen, which is the next element up. Some other elements split apart like uranium does. I'm trying to think of some other one. Like a lot of the radioactive ones, especially above 80, above lead, which is like 82, I think. They'll start to decay down to there. In general, so carbon-14 is a type of carbon that will decay into an element, like I just explained. We'll move into nitrogen, which is the next element up. And what we look at is what is called the half-life, okay? So all radioactive isotopes all have a half-life, and that meaning that that's the time it takes for half of an element to be gone. And so if you notice up on carbon-14, it has a half-life of 5,000 years. So not only is this is probably the most common one, carbon-14 is used in dating. Okay, so when we want to date something that's man-made, we'll say, okay, we'll look at how much carbon-14 was in it, because it's not changing the amount that's in there, so it's going to decay down and give us a good estimate of how long it takes for it to go away. And so if you notice, it has a nice, beautiful curve here that follows it down to 0. And so it's not much good after about 30 to 40,000 years. It gets kind of wonky. But again, it's kind of where it is now. So compounds. So what a compound is a substance that is a combination of two or more elements that are bonded together. So you take two elements, put them together, you get a compound. So like for example, a compound will always have the same number of elements. So like for example, water, H2O, will always have two hydrogens, one oxygen. Glucose is the compound C6H12O6, will always have 6 carbon, 12 hydrogen, and 6 oxygen. So that's will be consistent throughout. If it's glucose, it's going to have those type of numbers on there. So the compounds will always have some properties that are different than elements that make the compound. We have some of the properties, the same properties. Have some properties that are different, so they have some that would be similar. So another thing that these are what compounds are, they're chemically put together. and they're bonded. Where we use the word in chemistry is the word bonded, meaning they're sharing electrons or trading electrons or whatever. But it cannot. But you cannot take a compound apart. Like for example, the glucose at the top here. You can't break glucose down unless you have a chemical process. Okay. So I can't change glucose into anything else without having to go through some sort of process. One common process would be burn. I could burn sugar, and it'll turn into carbon dioxide and water. A chemical bond, okay, is where two atoms move their electrons around to create a stable outer energy level. So they're doing the outside energy level. It's stable. And that's why they want to move electrons. Because remember, electrons are moving around the atom. So the only thing is we can share between elements is the electrons. We can't share protons, because if we start sharing protons, we start changing all sorts of stuff with it. It becomes a whole new chemical. So a covalent bond in this case is where the atoms share a pair or two electrons between two atoms. Okay? Both atoms have the benefit of having their outside energy level. That's what we're looking at. Is the outside energy levels are full, okay? Are full or empty depending on the kind of bonds. So you've got So you got three types. You got singles, double bonds, and you got triple bonds. And so like a single will share 2, a double shares 4, and triple shares 6 electrons. So when we have a bunch of atoms that are together by covalent bonds, they're called molecules. Okay? So a molecule is everything with covalent bonds. Now, sometimes that one atom wants to empty out because I'll just go ahead and tell you, atoms either want to have a full outside energy level or an empty one. Okay? And sometimes you got some atoms, like lithium, for example. That's why you don't play with metallic lithium, is because it so wants to give up its outside electron, because it's full underneath of it, it would readily give that away. And other compounds like fluorine, which is one electron away from being a full outside energy, that it would literally take an electron from something. So here's what happens. Like if I take the lithium, and what I'll do is I'll literally transfer the electron to the fluorine. So we can say that one atom, we'll say it this way, that one atom will take an electron from another atom, so both can have the outside energy levels stable. And in some atoms, like magnesium, will give up 2 electrons. Aluminum will give up 3 sometimes, because it's easier for them to give up the electrons than it would be for them to fill it up or even try to go through covalent bonding. So what happens is that makes the atom an ion. So an ion is basically an atom that has a different number of protons and electrons. If I've got more electrons because they're negative, it's gonna, so a positive ion. So this one we lose one. So we'll just say it this way. This one, since it loses an ion, so I have more positives. So this is a positive ion. This one has more negative because we got an extra electron. So we got one more electron. This one has one less. This one is a negative ion. Well, what do you know about electricity? You always heard the phrase opposites attract. Well, this is what happens here in atoms. They get a positive, looks at a negative, they come together. That's the natural course of things. So they come together, and because they got a positive balanced out a negative, they're happy like that. And so they'll make a bond. So when a positive ion and a negative ion comes together, they form an ionic bond with it based on the electrical forces. So like I said, the positive negative comes together. And so let's talk about what happens when you have like elements and compounds that are already together. We've got some things together. So we're looking at van der Waals forces. A van der Waals force are weak attractive forces. Okay, so they're very weak. And these are, you'll find more, we talk more about van der Waals in a bunch of molecules that are covalently bonded together. And so sometimes you got regions that are a little more positive, that are a little more attractive to the electrons than the other ones. Like, for example, when you have a hydrogen that's got one electron, it's okay to kind of like be by itself as a proton, and let the oxygen kind of use the electron, and so the electron kind of holds those two electrons together, has a temporary kind of a negative thing. So they call that, we got a molecule that has a region that's positive and a region that's negative. I'll show you on the next page. But those are called a dipole, okay? Because the atom itself, or the molecule, I should say, has a region that's positive and a region that's negative. And so, like this here, the electron tends to go this way. It's still bonded covalently, but it spends more time up here. Okay, so it tends to be, we use the term delta negative, delta positive, and they use the lowercase delta, which looks like an O with a little squiggle on top. Well, this positive is going to attract the negative that's on the oxygen, and again attract this positive that's on this positive. Got the negative here, and I've still got the positives here, the positive negative, and those positive negatives attract each other together. And this is specifically done with hydrogen because it's just a pure exposed proton. Okay, so again, let's just kind of talk about this for example. When you look at when electrons spend more time with one atom than the other, it's called a polar bond. And so remember that the electrons are cloud. We use the term a cloud. And so a polar bond with hydrogen just kind of pulls that circular cloud away from that hydrogen, kind of leaving that little proton exposed. So you got that pure positive thing kind of pointing out there. And so what happens is that water attracts another, again, like I've got up here, it attracts another water, and they form tight bonds, okay? And they're very tight. And for other compounds that are the same size as water, water has a molecular weight of 18. And another compound that's really close to that, methane, water, we know, boils at 212 degrees Fahrenheit. Methane, give me a second. of methane is negative 258 degrees Fahrenheit. And they're about the same size. But because of these hydrogen bondings, okay, because they form that tight bond with the water with itself, that's what allows that water to have those unique properties that allows life to survive, because water is necessary for life. And so when we're doing polar bonds with hydrogen, we call those hydrogen bonding. And so that's kind of what we're doing here. We're using the hydrogen specifically. I hope that gives you a good introduction into atoms, elements, and compounds. Have a good day.